So, hello. So today I'm going to talk about some software that we wrote that connects something called active machine learning and crowdsourcing. And I'll explain what this is and why it's useful. But I would like to note that in the last talk in this room, someone asked the creator of some satellite Earth imagery, the API for Earth, he asked the speaker if the DoD and the Air Force came knocking. And it turns out they've been knocking at our door, and they've been using our software. So before I start, I'd like to mention a couple things. First of all, I'm a grad student at the University of Wisconsin-Madison. I study machine learning and optimization. And I think I get a little too anxious about the links to slides. So I have a link to the slides right here. It's also the last thing I tweeted under the SciPy 2017 hashtag with my handle there. And it will be available on the bottom right on every slide after this. Okay, so we have written some software. And our software, it addresses a problem. I don't know if it solves it. The problem it addresses is one of a problem common in the classic machine learning workflow, the problem of data collection. In the classic machine learning workflow, we sort of assume that the data has already been collected, and some complex mathematics is used to produce some result. What we have said is what we have and others have said is that if this data collection process is expensive, we may want to use some of this complex mathematics to help this data collection process out. A good analogy I heard yesterday is that if machine learning is some really fast race car, data is the fuel that can make that race car go, which means that data collection is the gas station. And if gas is expensive, as it often is, we may want to optimize for cost. This data collection process is often expensive in crowdsourcing. This is where we ask many humans questions, typically via some web interface. And then after we collect the results, we download the results and produce some useful machine learning model or something. An example of this is with the Google's "I'm not a robot" prompt. In this, they present some image that says, here are some numerals, and they ask you to type those numerals. After you do this, you go on your way and do whatever, but you are secretly a crowdsourcing participant because your responses are being used to train some machine learning model, eventually, to train some machine learning model to predict the text that you just typed. However, I'm not Google, and I can't ask all these questions. I need some way to require fewer responses, preferably minimal responses. Can you hear me, by the way? All right. So I'm not Google. I don't have the resources. I don't have some page that gets billions of hits each day. I am just some experimentalist at Madison that wants to train some model with minimal responses. That's all I have. So that's our goal, to use minimal responses. That's the main goal behind our software. The way we do that, one way to do that, is by adapting to previous responses. And this is the study of adaptive data sampling, if you've ever heard of it. In this, we say, so a passive workflow, not adaptive, just says I'm going to decide which questions to ask those questions, and get some result. In the adaptive workflow, all we do is we adapt to that result. We say, given this result, what question should I ask next? This is useful because it puts the human in the loop. It determines, at the end of the day, humans are determining which questions are important. And it requires fewer responses. So there's a lot of study behind this, and it's useful in other contexts, but our goal is to bring this to crowdsourcing. There are some benefits to this, and they're shown here. So I'm plotting the data collection cost, like the cost of crowdsourcing, the cost of actually collecting the responses versus problem difficulty. And we see that passive algorithms that do not adapt to previous responses are far more expensive than adaptive algorithms that do use previous responses. A quick example of this is with sorting. A passive sort requires order n squared responses. An adaptive algorithm like quicksort requires order n log n responses on average. So existing crowdsourcing systems like Mechanical Turk or SciTurk or any of these, they don't have the data flow required to even supply to use adaptive algorithms, right? So adaptive algorithms require some callback after someone responds to update how important each question is. Mechanical Turk and all that, they don't have that callback. We do. So given perfect responses, we can realize some benefits, as shown here. This is important because it saves money, right? And it mostly it enables research that was not previously possible. I mean, the reason that Next was created, our software was created, was because some psychologists had some problem way over here, and they couldn't do it without our system. So they said, hey, how can you help us? And we said, okay, give us a while. And then we came back with the system. So it's important. This software brings real benefits. It enables research that would not be previously possible. All right, so those are the benefits of adaptive data sampling, but I want to show a more clear example of, or a more useful practical example of what it looks like. So let's say we're labeling fruits, and we have labels apples and oranges, and we're on two axes, maybe height and weight or something. And we can draw some classifier on the middle that separates apples and oranges. Now, the adaptive data process says we want to collect a new result. And let's say that we want to collect this new result that, in some sense, it will give us the most information. One way to do that is by saying, where are we most uncertain about the label? And one of those cases is right here. It's about halfway between an apple and an orange. After we learn that the label is an orange, our classifier changes pretty dramatically. If we collected a label far away from where we are pretty certain on the label, that wouldn't be the case. Our decision boundary may not even change at all. All right. So this is adaptive data sampling and provides real benefits. We want to bring this to crowdsourcing. To do that, we have developed a software, or a software system. We call that software system Next, and today I'll be presenting joint work with Lala Jane and Daniel Ross. That's the work. We've made the system hopefully easy to use. But of course, we were helped by Kevin Jamison, who helped create the system along with Lala, and Rob Nowak, the professor who helped enable the system. At one point, we all worked for him. I have the pleasure of working with him. Everyone else has graduated onto bigger and better things. I would also like to thank our funding agencies. Without these groups, the software would not be possible. So our software is pretty widely used, and in one case by this Air Force research group up in Rome, New York. They're doing some active image classification with the group led by Lee Sievert. But the more interesting case is with the practitioners, because they have some real problem that we can actually look at. And one of these use cases is with the New Yorker. So the use case with the New Yorker is they have some cartoon caption contest. And in this, the person who runs this, Bob Mankoff, he receives some contest from his cartoonists. And this cartoon doesn't have a caption. So he asked his readers for funny captions. He received something like 5,000 captions from his readers. And most of them are pretty unfunny. It's true. So he has to find the funniest one. How does he do this? I mean, it's difficult, right? Because humor is hard for computers to predict. So this is a problem meant for adaptive data sampling because we have many, many captions, so it's a difficult problem, and we have limited human responses, right? So we want to find the funniest caption with confidence. Using a passive algorithm, we can't. Okay, so the interface, so our software now runs the cartoon caption contest each week, and the interface we present is shown here. It's available at these two URLs, but it's also shown here. So we give some cartoon, and we say, here's one caption that goes with that cartoon. You can rate that caption as unfunny, somewhat funny, or funny, and after you do, the buttons turn gray for a while, and a new caption shows up. The way this new caption shows up is what I study every day. This is some mathematical algorithm that's in my head, and in a paper too. Although it's not mine, it's Kevin Jamison's. I want to make that clear. So it is some complex mathematical algorithm, but the way it chooses The intuition behind the math is more important than the math. And it's trying to find the funniest caption with as few responses as it can, right? So what it does is it says, I want to devote all my responses to the funny captions so I can find the funniest one. I don't want to ask about all these unfunny captions, right? So, oh, this is a video. This is a GIF.
Yeah, I understand the video.
Oh, this is me. I took a screenshot. The question was, who's clicking? And I just answered it. So if a caption has received nothing but unfunnies, it's probably not that funny, and we probably shouldn't ask about it. Why waste? Something like a third of all captions are receive nothing but unfunnies. Why should we waste human responses on this? We want to find the funniest caption. It doesn't make any sense to ask about this. Okay. So this is the interface we present to a crowdsourcing participant. Now, what interface do we present to Bob Mankoff, who is running this experiment? So we say, here's a web page that describes the state of your caption contest. And he cares about the funny captions, so we list the funniest captions as determined by some algorithm. So the funniest caption for this person grilling your briefcase is, I'd better give it a little longer. It's a really tough case. It's not bad. He also sees some other basic information, like a histogram of when people responded, and some stats that describe his experiments. So we see that he sent an email to this interface right about here, and that we've collected about slightly less than 500,000 responses for this contest. Now, you might say that this data could be valuable for a machine learning researcher, and it is. And that's part of why we created this system. We've collected something like 20 million button clicks to 350,000 unique captions over a year and a half. And we're using this data set right now for some machine learning research projects. And that speaks to the larger goals of the system, which are shown by this slide. So we had some collaborators. So we study adaptive algorithms, and we had some collaborators in psychology that use crowdsourcing, and we wanted to enable some feedback loop. We wanted to tell them, hey, you need fewer responses, and they could tell us, hey, here's the data we see and the problems that we see with it. This is important because arguably some of the deepest insights and greatest innovations have come through experimentation. We want to enable this. The only way to do that is to make our software easy to use. This allows a low communication barrier, meaning that, this feedback loop wouldn't exist if no one used our software, right? So we want to make it easy to use, and that's what I'm going to describe next. That's the rest of my talk. But first, I'm going to describe what our software can be used for. And it can be used by default for one of 3 applications. I should note that our software is pretty general. We can use any application, any problem formulation, as well as any adaptive algorithm. By default, we supply 3 interfaces. The first one is with the caption contest, as you've already seen. In this, we ask about one item. This item can be, anything that HTML can display, images, text, video, whatever. Our adaptive algorithm does not care. And it's called cardinal bandits in the adaptive algorithm literature. The second interface we present is called dueling bandits. In this, we say we have adaptive algorithms that support finding the best item in some set. So we say pick the best item, pick the better item of the 2 shown. In this use case, which involves one of my lab mates and someone who studies economics at UChicago, it's rating the safety of city streets in Chicago, so they can have some map of how safe people perceive streets to be. The third application we support, and the one that was the motivation for this entire software, is generating some similarity measure over some low-dimensional similarity measure. To do this, we ask how similar different objects are. So we say, which of the bottom 2 objects is more similar to the top object? So if you thought this face was more similar to this face than this face, you would say, you would select this answer to say that these 2 are more similar. I should also mention All right, so those are the three applications that we provide by default. I should also mention that Next can also be used through a REST API. I mean, this is how the New Yorker interacts with our system. Okay, so that's what our software can be used for, and I've described most of the interactions with our software. I've covered how crowdsourcing participants interact with our software. I've described what our software can be used for, and that determines the question that these people see, the questions. And I've also shown how experiments are monitored. Now I'm going to talk about this last box here, the algorithm developer and the interface they see. This is me in my day job. This is what I do. I study adaptive algorithms. And any adaptive algorithm, the data flow requires at least 4 functions. The two most important functions are functions called getQuery and processAnswer, which is say, like getQuery is used when someone is waiting on a web page for an answer, and processAnswer is used to process their response. This is natural. So any adaptive algorithm is really just these 4 functions. However, designing these 4 functions is a little complex because we do depend on human responses, which means that we have to run some web server because we're doing some crowdsourcing experiments. And we want to provide some interface to some mathematician, which requires that we use, the entire NumPy, SciPy stack. But, so this is a rather large software stack, but we want to provide a nice interface for a mathematician. We want to make it simple and easy for them to, realize their mathematical statements. So we want to make it easy for them to use to design each of these 4 functions without worrying about, about Celery or Redis or Flask or any of this. All right. So to do that, we had to make a couple decisions, design decisions. So the first one is the most important one, and we decided to treat algorithms as black boxes, meaning that we put something in, we put a certain set of inputs in, and we expect a certain set of outputs back. This allows some mathematician that has 2 algorithms in their head to compare them easily because they expect the same inputs and they'll return slightly different outputs, nothing more. In practice, this means that we have to document and type check both the inputs and outputs to each of these 4 functions, which makes it useful for the mathematician because all they have to do is create some map between inputs and outputs. We don't care how they do it, we just care that they do it, nothing more. The second choice we made was that we wanted to use some, so most adaptive algorithms, they have to perform 2 tasks. They have to store values and they have to update some model. So what we said is, all right, we'll give you some wrapper around some database and that will allow you to run asynchronous background jobs pretty easily. So we give them this wrapper. The third decision we made is not really a decision, it's just a choice we made. And it's enabled by default in the default apps. You can change it if you want to, but I don't see why you would. That choice is we said we're going to abstract the objects we ask about, some images, video, whatever. We're going to abstract all of those to integers. This allows porting your algorithm to Next is pretty easy then. All you have to do is just use this wrapper, nothing more. It also abstracts like all the experiment details away from the adaptive algorithm. By default, every adaptive algorithm is agnostic to the objects it's asking about. If we didn't do this, everyone else would, and we do it. So we did it once and we did it right, and you can change it if you want to, but I don't see why you would. Okay. I should also note it makes testing easier, and we have tests. So there's more detail in the proceedings and in the documentation about how to use our software for the algorithm developer, but I also came here to describe how an experimentalist will use our software, because Next was born out of collaboration, and we designed Next so that some psychologists could use it pretty easily. So now I'm going to show, so I've described this algorithm developer box, And now I'm going to describe the rest of our software, or more accurately, launching the rest of our software. The only thing we require is we only require a web browser. This may seem, you may wonder why you may wonder like, oh, shouldn't I download some code? And you can if you want to, and you can launch it on your own cluster, all that. But we wanted this to work through collaboration, meaning that we wanted to enable psychologists to send some link to crowdsourcing participants fairly easily. One way to do this, the easiest way to do this, is through Amazon AWS and through the web browser. So after you make an account on Amazon AWS, you find their Elastic Cloud Compute Service, and you click on the nice big blue button that says Launch Instance, because that's what you want to do. And then you find our operating system, or our AMI, and after you select the right one, you configure the other details that are on the documentation. These other details are pretty small, like you have to select the right instance, and you have to you have to open one port and add some memory, but that's about it. There's more detail on the documentation, and please read it. But after you launch it, you see another web page. And this web page says, it really says only 3 things, these top 3 bullet points. And what it says is, the first bullet point is, here's some list of running experiments. And of course, you just launched it, so you don't have anything running yet. And we say, all right, then here's a link to launch an experiment. This requires the upload of 2 files, some file containing all your images to ask about, or text or videos, and some parameters that describe your experiments. You ask what goes in these parameter files and how they're configured, and we have examples as well as documentation that describes the parameters required or optional, the optional parameters for every application, each of the 3 problem formulations I showed earlier. Yes, okay. So that's all I have time for, but I do want to leave with 4 key messages. The first key message is that adaptive data collection can drastically reduce data collection costs. I mean, take sorting. That's one example. The second message, and so it can lower the barrier to collecting data, which is what we want to do. The second message is that Next is a crowdsourcing data collection tool that uses adaptive techniques. This is new and novel. Existing systems don't really do this because they don't have the callback required to say, update the responses or update the question importance. Notice I did not say that Next would lower your data collection costs. If your problem formulation is such that you get nothing but noise, we'll give you nothing. We can't do much. If you have some easy problem where you get really good answers that are very precise or very accurate and precise, then we can do something. The third message is that Next is easy to use by everyone involved. And there's no mathematical background required. Notice I put a star next to easy. This system was developed by an academic group for collaboration. So by easy, I mean that the psychologists we invented the system for are not in our face every week or every month. But we hope that for you, for Python developers, that you can use this system. I mean, the psychologist would come to us and say, we have to point them to what Python was before we told them to download it, stuff like this. The last message is perhaps the most important one, and it echoes back to our original, the overall goal that we want to enable this feedback cycle. We want to hear, so we developed Next to hear from crowdsourcing participants or people who use crowdsourcing, and so we want to hear both. So we want to hear to both aid research and improve the software. As such, we've created a Gitter channel on GitHub, and there's a link on our GitHub, and you should go to it and you should ask questions. You should describe your problem. You should describe what you expect to see. You should describe any solutions you may have, And we'll come back to you and say, hey, we've studied exactly that problem, or this is what you should use, or here's some papers you should read, or something like this. We want to hear about this. And so I guess with that, I'm asking for questions. If there are no questions, I have some extra material. So one question you may have been thinking of is, how do we acquire, so for the algorithm developer, or for this, for the experimentalist launching an experiment, how do we require that, how do we document and type check all the inputs and outputs? And the way we do it is through some custom YAML interface that we developed, that Daniel developed down here. And we say, we expect some string, so an example of this is, for some function called getQuery, we would say, we expect a string that represents the participant UID, and we expect you to return some integer that represents the arm to ask about. The implementation for this will look like, there's an extra self in here, but your arguments will be the wrapper as well as this string, and you can use this string to use the wrapper to pull the database. Yeah, that was my extra material. Oh, you have a question?
We'll let you have one. I guess the third application you mentioned where you compare two subjects to a third subject.
Yeah.
So, I mean, the way you use that, you use that for facial recognition, right?
So we use this to generate some similarity map of different facial emotions. So we said like, here's some 2D. Oh, so sorry. The question was, can you use the facial recognition for, or the similar?
This process for facial.
Yeah, right, for facial recognition. And so we use this to generate some two-dimensional similarity map of facial emotions. So we said like here's a bubble of the happy faces. Here's a bubble of the angry faces. Here's a bubble of other faces. Yeah. It's also been used to generate the similarity between different types of alcohol. Yeah, that's all I have.